Today's paper is about a problem that involved one of the most famous physicists of the past century, Richard Feynman. When Feynman was doing his PhD at Princeton around 1940, there was a problem in a hydrodynamics book that was circulating around campus, and basically all the students, the physics students, were discussing it. The problem was something like this. So if you have a lawn sprinkler, with a shape similar to what I have here, if the sprinkler sprays water, everyone knows that it will go around rotating, backing away from the outgoing water. So something like this. Now, if we completely submerge the sprinkler, and instead of spraying water, we suck water in, the question is, in which way would the sprinkler turn? So Feynman, being Feynman, he went around campus and tried to talk with as many physicists at Princeton as possible, just to find out that people thought that the problem was trivial and were reaching with the same level of confidence at completely opposite conclusions. So some physicists were saying that it was obvious that the sprinkler would turn counterclockwise, while others were confident that it would turn clockwise. Feynman also claimed that after he figured out the answer to the problem, he went on and tried to experimentally test it at the Princeton cyclotron lab. The problem was that when applying pressure, the sprinkler exploded, and Feynman never publicly revealed his answer to the problem nor the result of the experiment before it actually blew up. So what we are going to do today is basically solve the sprinkler mystery left by Feynman. And so to do that, we are going to start by considering a sprinkler that is completely submerged. So this is one end of the sprinkler, this is the pivot point. And so the pressure outside the sprinkler is just the hydrostatic pressure, let's call it P1, that is equal on opposite sides of the sprinkler, P1, and so the pressure inside the sprinkler, let's call it P2, is in fact lower than P1 because water is being sucked into the sprinkler, and since water flows from areas of higher pressure to lower pressure, P2 is actually lower than P1. Since there's a pressure difference on this wall, there's going to be a force applied on the wall, and the force is in this direction, and the magnitude of the force is proportional to the surface area times the pressure difference, P1 minus P2. So at the same time, we have water that is flowing down the sprinkler and with some velocity and is going towards this wall. When the water hits this wall, it will apply a force on the wall that is going to oppose the pressure force that we have here. So the question is, what is the magnitude of that force? To calculate the magnitude of the force due to the velocity of the water hitting the wall, we are going to consider the water flowing down a pressure gradient. So as we can see here, over a very short interval of time, let's say an infinitesimal chunk of water is going to travel from an area of pressure P to an area of pressure P minus delta P. If the water is flowing down a pipe of cross-section A, the momentum gain per unit of time, so per unit of time, is going to be equal to the force, which is equal to area times of the cross-section times delta P. So now if we integrate this expression over the entire length of the pipe, the rate at which the water gains momentum is actually A times P1 minus P2. So this momentum is going to be transferred to the wall when the water reaches the wall. And as we can see here, this force that the water is going to apply on the wall is exactly the same magnitude as the pressure force that we calculated a few moments ago. So what this means is that these two forces, since they have the same magnitude but opposite directions, are going to cancel each other. So the net force that is going to be applied in the sprinkler is actually 0. So the sprinkler shouldn't move. Now, the problem is that there is a very important piece missing in this puzzle. So far, we have considered water to be an ideal fluid with 0 viscosity, and that there is no energy dissipated when the water is flowing down the sprinkler. And now, if we consider that there might be some energy that is transferred from the water to the walls of the sprinkler, and that the water actually can lose some energy, this means that the force that the water will exert on the wall as it reaches the wall is going to be lower than A times P1 minus P2. So what this means is that the net force applied on the sprinkler, since these two forces are not going to cancel each other anymore, since this is actually going to be a little bit, the magnitude is going to be a little bit less than this one, there's going to be a net force pointing in this direction. This net force will generate a torque that will make the sprinkler rotate towards the incoming water. So this effect is actually really important in a real-world situation, as we can see in this experiment done at Harvard, but with air flowing through the sprinkler instead of water. As we can see, the normal sprinkler will move as expected, backing away from the outgoing air. However, in the case of the reverse sprinkler, it will turn, moving in the direction of the incoming air. So there you have it, the solution to the famous Feynman Sprinkler problem. If you enjoyed the video, don't forget to like and subscribe to the channel. Also, if you want to learn more about this problem, you can click on the link to the paper in the description. Thank you.